Well, I got some really good questions over the break, none of which I could answer because they were so good. When I'm presenting these models, they're flamelet models, and so they automatically don't apply to a lot of the problems that many of you are looking at and studying. For example, I got a question about ignition. Okay, that's a really important question area. I'm not sure that you can use a wrinkled flamelet idea to explain everything about ignition. You can just imagine a spark plug igniting a whole region, a small region, but fairly uniform region with radicals, and then at some point it starts reacting and a kernel develops and it becomes a turbulent flame. So I would hope that in the later stages it looks like a wrinkled flamelet, but in the early stages it probably doesn't. So I think we need a completely different model, and I don't think anything I'm saying here will help. The other one is mild combustion, which is it's an idea where you take a lot of recirculation of exhaust gases and you mix it real quickly with fuel and oxygen, sort of like a well-stirred reactor. And then some people even use a lot of radiation because if it's rich, there'll be a lot of soot and it's radiating heat to the walls. And the radiation will help to keep everything uniform because the heat will radiate to the walls and the walls will get all red and radiate back. And so it's a nice, you know, like you think of a black body device where everything is in equilibrium and it's well stirred. There may be flamelets in such a device at some point or in some places. We don't really know, but the well-stirred reactor, mild combustion, could be a different way of getting low pollution and good efficiency in furnaces and other devices. And so it has been pushed and it's been studied. I know Professor Heinz Pitch, Aachen, has done computations on mild combustion. But it does require a lot of recirculation and a lot of preheating of the gases. Otherwise, you get flamelets. So it's not really clear where flamelet theory breaks down and distributed well-stirred reactor theory should take over. But even with a well-stirred reactor, you have to know what the equivalence ratio is in the temperature in your well-stirred reactor, right? You can run that on ChemKin, but you have to give it a temperature and a fuel-air ratio, and you know, in a real device, it's hard to model something with a well-stirred reactor. So those are good questions. Unfortunately, the field is still stuck on these simple problems like jets and co-flowing jets and jets in cross-flow and Bunsen burners, and maybe in a few years we'll get on to these other issues. Okay, with the Bray flame surface density model, it's pretty much the same thing as we've been talking about before. You need a shape of the PDF, which is mostly bimodal. You need state relations, which you assume laminar flamelets equations, which can be either unstrained laminar flamelets, which in other words, very low strain rate flamelet on ChemKin, or you can run a strained flamelet on ChemKin and get these state relations, which go in here and then are used for time averaging. And then you generate now tables in which the mean properties are functions of these two other variables, C bar and C, and the variance. So the lookup table, I didn't put the proper symbols on top here, but the lookup tables are between the mean density and the mean reactiveness and variance. Okay, so you've done all this integration and you get these lookup tables, and then you can quickly determine solve the equations. To get into this, flame surface density approach, I'll once again put this equation up. This is just for a laminar flame. It's in the coordinate system of the flame, and so the gas is coming at it at a speed s sub l, the laminar burning velocity. The temperature is going up in the x direction because of diffusion, diffusion of heat back from the products into the reactants, and then a reaction rate term. And same is true for the products, except they're going in the different they're going up and the reactants are going down. The temperature is going up. So let's see, yeah, the products are going in the same direction as the temperature, and that is up. And so you get a similar relation. Now the state relations will tell you that the species of mass fractions are related to each other. So if the products are going up, that means that a certain fraction of the products are nitrogen, oxygen if it's lean, water, and CO2. And so they all go up proportionately, and you can all get that from this fast chemistry relation. Okay. So again, the idea is we only solve one differential equation, and then for the laminar flamelet, and we can then get C, and then we can use the state relations to determine the other properties. Okay, and so this is just something you get out of ChemKin. My students working with me have plotted this. This is the temperature going up from reactants to products, and we non-dimensionalize it and call it reactedness. And then the OH curve is something that goes up and then reaches a steady value. That's the OH is only formed once the reactions start. Formaldehyde is this curve, and it's formed in this region, but it diffuses upstream because all species diffuse in both directions if they're intermediate species. And so this formaldehyde will diffuse upstream, and you can get these lookup tables. Now, when Bray did this analysis in the beginning, he wrote something like this. He said that there's a rate at which the temperature goes up, but then there's also turbulent fluxes of temperature, which are given by these correlations. And you can get them, again, by looking at the state relations and the PDFs and compute these values. So that was part of his analysis. But then the reaction, this is all now for the turbulent case where he's done the Favre averaging. The reaction rate here is the big problem. And this is kilograms per second of products produced per cubic meter. So it's a point measurement. At each point in space, it's a point quantity. At each point in space, this quantity is defined, and it's per cubic millimeter. And he argued that it's related to the flame surface density if you assume that there are premixed flamelets oscillating around. And so, again, as I said earlier, there are two issues here. Making sure that the reaction rate is right, and making sure the diffusion of species is right. And you could just relate this to a turbulent diffusivity, or you could try to be more exact, and that's what he did. Okay, so he actually tried to write an equation now for essentially the diffusion term, okay? And so he Again, he says that it's a quantity that can be convected and can be, it can diffuse itself, and then it can be produced and be destroyed. It gets pretty complicated when you do that, because you can do that with any term at any level, but this is a higher moment which he models with this equation. And actually, this paper here by Masuya, he's in Japan. He's a very active researcher today. He worked with Ken Bray, who's retired, and this is back in 1981. They did a really nice analysis of this premixed turbulent flame. Now, I sketched this. If you have a PDF, it's a bimodal PDF, but it's a PDF that depends on both the velocity and the reactedness. So if we look at C, the non-dimensional temperature this way, we say that we have C equals 0, and we have a spike at C equals 1. These would be reactants, and these would be products. But then we have velocities in each of these regions. So you imagine all the gases coming towards the flame have a certain velocity field and velocity fluctuations. And so this curve here is what Bray would represent the velocity field in the reactants. And so it's a Gaussian. It has a mean velocity, and it has a variance, which is the square of the RMS velocity fluctuations in the reactants. And so this U prime, actually this square root here would be considered to be the turbulence in the reactants, okay? It's conditioned in the sense that it's only when you have reactants that you compute or measure this velocity fluctuation. But then when you happen to be in a region where there's products, you will also have a bimodal a Gaussian distribution of the velocity field. But here now the mean velocity will be a lot larger than over here, because the gases have accelerated. The density is much lower here. And now we have a mean and a variance, and the square root of this variance would be the RMS velocity fluctuations in the products. And so this is the turbulence in the products. Now, if you say, what is the turbulence level of everything at a point? So if you just sat at a point and measured the turbulence, the velocity fluctuations, what you would do is you'd get a number that is a combination of the turbulence level in the products and the turbulence level in the reactants. And it would also depend on the two mean values, because suppose you're sitting there making a measurement and this flame is moving back and forth. Sometimes you get the mean velocity of the reactants, and sometimes you get the mean velocity of the products. That will contribute to the velocity fluctuations at a point. So when you say the turbulence level in a premixed flame, you have to be very careful what you define to be turbulence level. The right way to define the turbulence level in a premixed flame is to say, when the reactants are present, what is the mean of the velocity field at that time, at those times? So it's a conditioned turbulence level. Okay. And once again, you would take the laminar flamelet solution and put it through this type of PDF. This is P of C. And this is just an example of some of the math involved. It's fairly easy to do the math when you have a bimodal distribution. I thought I'd put this here just for fun, but I'm not sure it's any fun. Anyway, Bray was able to simplify a lot of the math. here is the velocity fluctuations. These are the reactedness fluctuations, the variance. And it's defined as C minus C bar squared bar, okay? And then you put that, you multiply that by the PDF, and you get, you put C minus C bar squared, P. But now the PDF is just A times the delta function centered at 0, and B. And A and B have to add up to be 1, and A and B are related to the mean reactedness C bar, which I don't have here. But anyway, when A and B are related to C bar with this quantity, and therefore when you're done here, you get that you get a simplifying formula that says that the variance, or the fluctuations in the reactedness or the temperature are related to the mean temperature, and that's because of this simple PDF. Anyway, what Bray did was greatly simplify the whole analysis by using this bimodal PDF, and therefore he ended up with ordinary differential equations because he considered a one-dimensional turbulent flame where on the average the flame is flat, but it's got all these wrinkles within it, and it's kind of nice to be just solving ODEs because then you can put it on MATLAB and push a button and you're done. But you still have this reaction rate problem. And so he started out with some unrealistic assumptions, and when he started working with the French, they came up with a much better approach, and that is to determine the flame surface density, which is proportional to the reaction rate, by writing this equation, okay? Now, again, anything can be written as in terms of a convection, diffusion, source, and sink. And flame surface density is a Gaussian function that sort of tells you where the flame brush is in space. And if you attach it to the coordinate system to the flame, then you don't have any unsteady term. If you want to do another analysis and attach your coordinate system to the engine, let's say a diesel engine where this is, or not a diesel, but a internal combustion engine where the flame is moving through, then you'd have to put the unsteady term, and it would simply allow this Gaussian to move through space at the turbulent burning velocity. But in this case, I've written this equation for coordinates that are attached to the flame, so it's just sitting there, and the gases are coming at it, and this U tilde is essentially the turbulent burning velocity, and we have a diffusion term, and there's a source term, and a sink term. Okay. Now, that will tell us what sigma is as a function of space, and that will allow us to solve these equations. A very nice paper was written a long time ago by Jay Gore, who worked with Jerry Faith and his graduate student Prasad. They took this analysis and applied it to a Bunsen flame. And this is a RAN simulation, so it's a long time ago and very simple, but a very nice paper to look at to understand simple models. So this is the coordinate system is attached to the burner, and so this is the conservation equation that they wrote for C tilde, which is the non-dimensional temperature, and it's two-dimensional. There's X and there's R, the radial direction, and they have a diffusion term and a reaction rate term. So this is standard stuff, and here is the flame surface density equation, which allows them, this W dot is a function of sigma. They have an axial momentum equation, a continuity equation. They need a turbulent kinetic energy equation, which they have in their combustion flame paper. And let's see, did I put any more? No, I didn't. Okay, I didn't put any more equations. There is an epsilon equation that looks sort of like this, and I didn't write down, there is just a simple linear relationship between the reaction rate and sigma. So if you look at all these equations, they're closed. You get C here, you get sigma here, you get U here, you get, the continuity gives you the radial velocity, and the K epsilon equations give K and epsilon. Now, you do have to put in these three terms. These are the rate at which flame surface is created and destroyed. And this term here is a stretch rate term, and this is a merging or dissipation rate term. It's proportional to sigma squared, because as the flame surface density gets large, things get very compact, and they argued that the flame merges and disappears. Anyway, with this analysis, they were able to get very nice simulations of a jet-like premixed flame. So this is premixed here. It burns sort of like a jet, and then there's products out here. And they did have some freedom to choose these quantities, and there are a few other things here, like this is a Schmidt number, and so they explain how they did all this, and they end up getting a mean temperature as you go across in here, and as you expect, the peak values that are on either side. And the main thing, though, is that if you do this at different heights, you can sort of get an idea when these two come together. There's another one up here where it's sort of like this, and that's up here at the tip where you call it the flame tip. And so they have another graph of that, and so it predicts the height of this fairly reasonably with the modeling assumptions they made, and so therefore they're essentially getting the right overall burning velocity. Now, I would call this an engineering model. It's first a RANS model, and they have a lot of adjustments that they can do to make it work right, but it gives you a lot of understanding of how to simulate turbulent flames. But in these equations here, there's no chemistry. Okay, they didn't make any attempt to get any chemistry out of this. They get temperatures, they solve for densities, and they get velocities, but they didn't make any attempt to do chemistry. And so the filtered tabulated chemistry LES is the modern approach. This is very recent, and the paper that I think is the best is one by, again, Vainant, and it's fairly recent, and they apply this to the Cambridge stratified flame burner, that burner I showed with a concentric premixed streams, all different fuel-air ratio. And they're using the following approach. They say that basically the reaction rate, which they call the subgrid turbulent burning velocity, but it's the reaction rate, is a product of the flame surface density, and they call it this for some reason. Everybody uses different symbols, but this would be something like a flame surface density, and then this is this integral of the reaction properties for the laminar flame multiplied by the PDF. It's a little confusing because they use totally different symbols than Bray did. I guess it's the French versus the British or something. You know, they all have to use different symbols. But it's basically the same idea. You have to get the new flame surface density from a flame surface density equation, and you need to then use flamelet ideas to stick it into the integral. But here they can use complex chemistry when they do their laminar flame lookup tables in state relations. So again, this is their LES simulation. It looks really beautiful, and you know, as you go up, let's see, this is at the base. As you go up, this brush region is getting broader. This is the temperature, and they did in this paper compare to the experiments done at Sandia, again by Rob Barlow, and everything looked pretty reasonable. Okay. So back to, somehow I jumped to the wrong one here. Oh, okay. Well, I guess I'm done with this particular subject, so I was going to stop today because it is getting kind of late. Why don't we have more questions? And I think the best thing to do is I'll be here for the next half hour, and we'll discuss this right here. And anybody else can call it a day. And tomorrow I want to move on to another subject. And so why don't we quit, and I'll see anybody up here who wants to ask questions.